Okay, so before we move on to the part 2 of the fundamental theorem of calculus, I thought it'd be worthwhile to spend just a little bit of time exploring what I like to call an area so far function that we see in the part 1 of the fundamental theorem of calculus. So let's consider this function. G of x equals the integral from 0 to x of the very simple function t dt. Okay, so consider that function. And you see this type of thing in the fundamental theorem of calculus part 1. So let's consider this function. Let's use geometry. Okay, before we do that, sorry, I'm getting ahead of myself. Let's look at what this function t looks like, and g is going to be the integral of that. So let's look at, we're going from 0 to x, which I'm not concerned with right now, but I want to graph the function y equals t. So the y equals t function. So all that means is that, for example, if t is 1, then y is the same t value 1. If t is 0, y is 0. And so if t is 2, y is 2. And so you start to see, hopefully, that you just get this perfectly diagonal line, y equals t. So the y value is the same as the t value. Okay, very basic function. And so what I want to do is consider examples of the g function now. I want to evaluate the g function. So let's say I want to determine, we're going to do this all with basic geometry here, determine g of, let's say, 3. Let's determine g of 3. So g of 3 equals the integral from 0 to 3 of t dt. In other words, in this picture, I would go out here to 3 on my t-axis, and I would want the area under this line from 0 to 3. And we can see that's just a right triangle. The area of which would be 1/2 times the base length, 3, times the height, which is also, if you trace this over, remember the y values and the t values are equal, so the height would also be 3. And so what we would get here is 1/2 times 9, which is 9/2. So that's an example of how to evaluate this area so far function. This g of x means the area under the t function, for example, from 0 to whatever x value you choose. So this number 3 can change. The 0 stays where it is. So it's the area from 0 to whatever x value you want under this curve. And here's a primary example. Now, let's do one more numeric example. Let's say I want to determine g of 10. So g of 10, I don't have to draw the picture, but you can imagine g of 10 would be the area under the t curve from 0 to 10. From 0 to 10 of t dt, which again would be a right triangle whose base would be 10. So you'd have 1/2 times the base of 10. And the height would happen to be 10 also, again, because of the function we're dealing with. So we get 1/2 times 100, which is 50. Okay? So a couple quick examples to show you how to interpret this sort of function when you're going from a constant to a variable, and that upper limit of integration can change. Now, the next thing I want to do is I want to do this, determine g of x. The reason I want to do this is because the first part of the fundamental theorem of calculus tells us that this integral should result in an antiderivative of the t function. It should result in an antiderivative. And when it does, it's going to be in terms of x. Okay? Now, let's see what happens here. So when I say determine g of x, I'm also asking you to determine the value of this integral. And the claim of the first part of the fundamental theorem of calculus is that the value of this integral is an antiderivative of t. All right, so let's look at this. So g of x equals the integral from 0 to x of t dt. Now, let's erase our scale here. Let's eliminate our scale. And what we're wanting to do now is find the area under the t curve from 0 to x. So let's just say x is right there. And I want this area from 0 to x, not 3, but 0 to x. That's still a right triangle, okay? And the area of that triangle is 1/2 times the base length. The base length here is x. The height, again, the output of this function is the same as the input. So in this particular case, the height of that triangle is also x. And so what we get is 1/2 x squared. Now, my claim, remember, was that the answer here should be an antiderivative of the t function in terms of x. Well, if you look at an antiderivative of the t function, it's t to the first power. When you do an antiderivative, you raise your power by 1, and then you multiply the coefficient by the reciprocal of that new power. So look, the integral here resulted in 1/2 x squared, which is this antiderivative of the original function in terms of x. So you can see how easy it is in this particular case to understand what's happening with this first part of the fundamental theorem of calculus. And I chose a very simple function here, t, for 1, so we could easily do the antiderivative, and 2, so we could easily evaluate this integral using basic geometry. So I hope you enjoyed that and hope you better understand this first part of the fundamental theorem of calculus.